Is that recording though? Yes. That is recording though. Yes, that is definitely recording. Alright guys, what's up? Guys and gals actually. It's your boy Nick here, and today we're doing the Peltier effect. I know we all call them Peltiers, but they're actually called Peltier. The guy that invented them was French. But before we get into that, I wanted to talk to you guys about mediums. And a medium in the classical sense is something that's in between, right? It's in between up and it's in between low. Be honest with you, that's my life right now. You invent something and you think it's gonna be like this magical fairy tale that you live with, having this wild new invention that, you know, maybe it does something that something hasn't done yet. Let's say that it does. You end up following inventors for your entire life, studying their every moves, where they went wrong, where they went right. And as a child, you had your inventors that were your heroes. And my hero was Willis Carrier in air conditioning. I had to go to school when I joined Carrier to study, and maybe I'll bring my book out if it's out here. Well, I don't have it with me right now. But we had the book that we were supposed to read called Father of Air Conditioning. And I'll be honest with you guys, I've had a lot of struggles actually. And I was hoping to seek solace. Like one of the things that happens when you invent something is you suddenly feel very alone in the world. And it suddenly becomes a place where you know some sort of arcane thing and nobody else knows around you, and everybody knows that you know something, but they don't know what that something is. And for you as the inventor, it's an incredibly frustrating time because you just want to teach everybody what you just learned, but the reality is you just don't know what you just learned. And so to go read a book about a hero inventor, almost exactly 100 years ago, who invented what we now know as modern DX refrigeration, and then laid the absolute groundwork of chiller technology as we know today. Absolute framework. It's undisputable. The guy had to develop what he developed. Willis Carrier developed what he developed because it was a necessity of the time period. People had just invented houses, to a kind of standard that we might look back upon today and say, yeah, it looks like a house, pretty much. They just didn't have air conditioning. So in the summer it was incredibly miserably hot, kind of like it's getting to at this point again. But it was a necessity of the time. He developed this refrigeration because it was a necessity of the time. People were getting into movie theaters, shopping malls, and that kind of stuff were coming out. And these were large atrium areas that had no way to keep cool. And this guy went and invented it and laid the framework and the groundwork, and everything we know today is based upon that. And to open a book and read a book about this guy and realize that he completely missed out on this technology 100 years ago. It existed. Don't get me wrong, it existed, but it wasn't in the form that it is today and available to us like it is today. And I look back upon that, and we're now at like a turning point in DX refrigeration, air conditioning, anything that's using refrigerant again as a medium right now in 2023 is at risk. We have new energy regulations, we have concerns about fire. I'm going to talk about fire in another episode, and what I know and what everybody else knows. There's some concerns out there, and we got to be prepared for that. We got to have contingencies. So the times, at least in my mind, are necessitating a change, and I don't think that change is happening rapidly enough. And I hate to be the guy that like steps in and tries to intervene with a bunch of big people in the room. But we have to do something about this technology. And I hate to be the guy that sits down and literally has the intervention with an entire industry of VRF about this technology needing a revamp. So that's some of what's going through my mind right now. And it is a tough time to have watched like a hero of an inventor completely miss out on this technology. And this is a very difficult presentation for me to give to you guys because I am an air conditioning guy. And I've been through all the struggles that you guys are going through, and I've been in the heat, and I've worked in the heat, and I've worked with customers, and I've worked with customers in the heat, and I've worked with customers that struggle with equipment that leaks and gets to them damaged. And that's besides the point, though. The point of today, and I know that's a morbid subject, and we're getting off topic here, but it's something that I had to get off my chest. And my channel is live, raw, unfiltered. I mean, that's the way I am. But today's discussion, or side topic as it is, was a medium. And I think that's really important because a lot of you guys are starting to tune in that it may not necessarily be this technology that's changing, it's just the medium that we're using. And I want you guys to remember that as we go through this. I see things changing in this industry, and we're going to have to start thinking of DX refrigeration in a different way because there may be devices that allow us to transition to this new technology. It's in discussion. We're trying to figure it out. And there's some stuff that I have in the presentation today that the functional analog isn't 100% complete. We have ideas as to what the last little missing puzzle piece is, as you're going to see. Some of you may know what the last little puzzle piece is, but we don't want to say anything. In science, it's called a confidence interval, and it's probably about 80% on what that last little piece is right now. But as we piece these things together, and hopefully we work together in piecing these things together, maybe we'll come up with some really cool stuff for the industry, and maybe everybody can find out how to work together a little bit better. That's my humble opinion. But that aside, thinking about mediums, thinking about refrigeration as a medium, I'm going to blow your mind real quick. So this is what I would call a medium, right? It's a can of R134A. And to me, this is just refrigerant. Now, today, to chat about some stuff, I brought my buddy Mysterioso over. And Mysterioso is, you know, he's an AE. He's an aerospace engineer. Something you would think is completely incompatible in somebody who would never look at refrigerant. And he picked this up off the table and he said, man, this is what we use in satellites. He said, wouldn't you use an ion engine? He said, nah. Ion engine, you know how big that power supply is? We'll never get that into space. We used R134A. I said, this actually, I see what you're doing in space now. I see this. It's just a different medium. I would have picked ions in space, but you picked refrigerant. This actually is just a different medium. It actually, I get it. This is like a battery, and it's just in a different state. So bear that in mind as we go towards the more fun part of the day, which is obviously explaining what this effect is on a silicon-based level, because, well, if we have a new medium, what's the medium doing, and what is this functional analog that Nick is talking about? And I'm going to get into that. We got to start thinking of, you know, maybe this one day might be our big jug of refrigerant, and maybe we might have plugs in the wall that already got refrigerant in them. It may not be that, you know, it may not be the absolute most efficient way of doing it today, but it's rapidly getting more efficient. Now, let me give you some preface there. So I have a highway with cars running on it, and kind of the subject of today is we might call an electron transport chain or a bias gate. And these things sound really scary, but you know, electrons tunneling, cars on a highway, you know, old fat man who works hard nut. We were talking about, it could just be puppies escaping a kennel. It's the same force of nature. So these things, like the medium, we're putting the medium through a force of nature. So let me advance this a little bit for you guys. So this is a Peltier. I'm going to call it Peltier because I'm a Texan. This is one of these little chips. This guy. And they're pieces of ceramic, if you look at them from the outside. The ceramic's there for a reason. The ceramic is an insulator. It's similar to the ceramic that you might find in Pyrex, or maybe like power line ceramic. It's a type of, it's conductive to heat, but it is completely resistant to electricity. So it's very thermally conductive type of ceramic. But that's there for a reason. And you'll notice that there's a positive and negative lead. And this is in this picture, it's energized. So you're supposed to know that the heat is transferring. It's rejecting heat out of the bottom. It's accepting heat into the top. And you see, yeah, ceramic substrate, solder layer. We're going to talk about that. Conductive pole, solder layer again. Now that's just a little kind of solder sandwich that's up there. And we're going to look at this thing much closer. And then semiconductor element. And when people see these things, these little charts like this, it's a turnoff for a lot of people. And the reality is, again, these are just what are called bias gates. And that's important to understand. And they even say N and P. So we probably already know from batteries what that means. But let's take a closer look. And you notice that it's kind of sandwiched. And it says electricity flow. And we kind of have this little zigzag pattern go. So it would look like, almost like we have light bulbs wired in series. And that's the reality. So let's go forward a little bit. Okay. So this is one of those little things that are in the sandwich. Now these things are called junctions. And there's actually quite a few of these that are on there, but they have to be built in a special way. And I'm going to kind of go into that with you a little bit, but not too deep. the way that they're built is special because these N and P junctions transfer heat in the same way, in the same direction. If these were stacked on top of each other, which from what I know from silicon manufacturing so far, that's a common orientation, and it allows you to do more things with traditional silicon in a computing environment. It may be better for that, but for transferring heat, this type of architecture is extremely, for the purpose that it is and where it's gotten so far, is an extremely efficient way of doing that on silicon. Reason being such is, in the air conditioning industry, the functional analog that we have so far is, this is an entire air conditioning system, each one of these junctions. And you might say, Nick, you're crazy. How is that an air conditioning system? This is an air conditioning system. You know, my air conditioning system is composed of a compressor that moves the refrigerant gas over here in this condenser, and I get rid of all the heat, and then it turns into a warm liquid, and it comes over here, and then it sprays out this expansion valve, and it gets cold because it goes through a phase change. And then it absorbs heat in here, and it comes back in here into the compressor to get pumped back up, charged back up again. Oh shit, did I use the wrong word? Charged back up. Uh-oh. This thing might actually be doing the same thing. What we know so far, and what we theorize so far, I mean, the working analogy is pretty close on this one, but the battery is now your compressor. This area is your condenser. This is where your electrons start riding a transport chain to go up. Now, really, these are what are called doped semiconductors. They are baked in an oven in such a manner that they form chains or strands in here where the electrons flux, because the electron doesn't actually move. And that's another critical thing to understand about mediums. The energy is being transferred. The electron isn't riding an elevator up here. The energy is being transferred up here. And as these electrons get to the top, they kind of settle. And while that may sound like a condenser, if you were to zoom into here, you would almost see where these, again, these were bimetallic junctions, so this is still a junction. There would have to be some sort of weld on a dissimilar metal. And a dissimilar metal, as we know from batteries, when those dissimilar metals like zinc and copper are put together, that makes a charge. So something very similar is going on here. We have energy that's transferred up. It settles down. Now, how is it cooling, though? And the reality is, these electrons are tunneling again. They're coming back down. The transfer of energy is coming back down through the electrons. And by doing that, it creates a cooling effect on the top. Not too dissimilar to an orifice. And the reality is, I'm going to show you scanning electron microscope images in a second, and the reality is it's getting to be a pretty close functional analog. And I say that with trying to preface the understanding of you can only have so much confidence in what a functional analog does, or what a functional analog is and to its extent. We're getting pretty confident that this functional analog is working because the principles of other things that we already know from other mechanisms are beginning to light up. So that's why, even as kind of scary and fast as things are moving, I want to slow down and try to teach people what I'm understanding so far. So anyways, the general momentum, as we might want to call it, or the transfer of energy, or the current, J, begins to ride down. And as it rides down, it creates that actual cooling effect. And again, not too dissimilar to a DXV, it would be up here. And that, if it were connected to a piece of metal, would cool that piece of metal. And then, as it comes back down, it's settled down and it comes back to the battery where it gets compressed for the next cycle. The reality is, this isn't moving. And that's the conclusion that I came to today that really, at least for me, opened my mind. This is not running water in a loop. It's a transfer of energy. It's a medium. And if we move over here, and this is going to really sound crazy, this is transferring energy as a medium. The refrigerant is getting compressed. We have a term that we use called heat of compression. It is generating heat, and the heat as energy is traveling through the system. Wouldn't it be a weird world if you removed the compressor and then heated a pipe to the heat of compression and then allowed that refrigerant flow to move through the pipe and condense and then even be passed through a check valve? What would happen then? You might even get cooling without a compressor. And that's the wild world that we're beginning to see. If we look down the barrel of what might come next, is a world of heat pipes that may be driven by solid state machines. But the reality is, at an electron level, we may have hundreds, if not thousands, if not millions of tiny little compressors doing the same sort of, you want to call it a phase change, but it could also be a medium that's a polarity change. How is it that different? Now, if we would want to label our parts, and here's the thermographics, by the way, before I even label the parts, because I promised you guys thermographics, right? This is a scanning electron microscope image of a p-n junction, which isn't the exact same thing, but it is a junction, and it's hard to find a cross-section of one of the junctions because usually they're looking for quality of silicon when they zoom in. So a lot of the pictures that you find are silicon kind of QC images and looking at a chip real close. This was looking at flow. And I thought this was very interesting because essentially to me, in my functional analog so far, we are compressing the electrons. The electrons are going through a check valve, or the electron flux is going through a check valve. The flux moves through here, it goes through another check valve where it starts losing its energy. And when we think of it as a check valve, it's an electron tunnel. It only allows the movement in one way. So functionally it's acting as a check valve. Settles down, releases its heat, moves back and gets heated up again, just like the heat of compression over here. So the reality is we have an energy completing a circle of life, so to speak. The compression cycle, you want to call it the adiabatic cycle, it's not, but we have a similar effect going on over here as over here. And like this chip in particular, 150 watt chip, has 127 of these little guys per every chip. And they're oriented in different directions so that all of these can be wired in series for the same effect. If you were to look at the bottom of these where they have the other sort of not non, but you have your other part of your junction that releases the heat. I was going to say non-cooling side, but it's an energy transmitter if you really want to call it that. But anyways, everything is bonded so that everything can be in series, so that everything can conduct. And due to the architecture of this not being on top of this, because if you put one on top of the other, the heat isn't going to flow through the device. Normally they're angled towards each other like magnets. So the heating effect cancels each other out and you don't get the heating flux or the very cool little heat pump device that we end up with. Now, talked about electron transfer. I want to relabel this real quick because when I started relabeling things, it made a lot of sense to me. And I even put where we don't know. We don't know where the condenser exactly is yet. We have a very good idea of what that is. And the reality is that the condenser may be in your condenser already, if you know what I mean. We don't know that yet. It's a theory. And it seems to be valid, but it hasn't been tested. And it might need a big condenser. So we're trying to figure that out. We know this is the evaporator. We know so far this is acting as the TXV. We know so far this is acting as the compressor, because that's our medium. We don't know yet that that's the condenser. I'm trying to find that out for you guys. So, over here, we may have the same thing, right? We have a P junction, which is our positive side, our hot gas. Got an N junction over here, which is the negative side, our cold gas. And then we have our cooled side and our dissipated heat side. Seems to make a lot of sense. Now, I can't say with 100% confidence interval that this analogy is 100% functional. That's why I go through a lot of stress every day right now. I have a good working analogy for this. Things are starting to light up. But the reality is, the shocking reality is, when you invent something you just don't know, you observe, and you record, and you become empirical. When you start seeing these things repeat, and you start seeing other patterns from other devices light up. So, for now, for me, the functional analog is functional until I find dysfunction within the analog. So that said, we compared these traditional heat pumps. We talked about electron transfer. We talked about the principle of the hot and cold side. We talked about similarity to how an HVAC moves heat. We didn't talk about why these things are inefficient. And we're going to get more into that later. And for those of you, like from the 90s, that might know these devices, I mean, these things in my life, for me at least, now I was pretty close to computers, but first time I ever saw one of these probably was around 1995. I want to put a mark on them. They were about this size. They were really bad. These are not nearly as bad as they used to be. But they came out in about 1995. Why are they inefficient? And there's a couple reasons why they're inefficient. Now, we're going to dig into the whole power thing here in a second, but in general, the reason that these are inefficient is that people drive these at the full power, and that's sticky. I'm sorry that I said that. It's not a great idea for a computer chip to run it at its absolute max power, or anything related to a computer chip, any sensitive piece of electronics like this. You want to run it at its most efficient point. People are not running these at their efficiency point, and that's why these have gained a reputation as an inefficient device. There, I said it. Point two, these got popular in the late 90s with computer gamers, which we're going to talk about that. That's fun too. Computer gamers. They started getting cheap in the 2005 era. But people would just buy these chips and they thought these were like heat accelerators. Like, I'm going to plug this in and whatever amount of heat, this square area is going to just suck it away. No, we all know in the air conditioning industry that you have a specific BTU amount that moves. And in this computer industry, it's watts, it's not BTUs. So you're going to have to translate back and forth a lot. But what people would essentially do is take a 200 watt processor and put a 150 watt cooling chip on it and scratch their head as to why these things would keep blowing up. So they gained a reputation of, wow, this sucks, man. Every time I put this on there, it doesn't even cool. And when it does, it doesn't cool very well. Why do we even use these things? Well, the reality is you bought the small one and the cheap one, and you installed it in such a manner that it doesn't work. And I'm sorry, Linus, but these things can be efficient. I disagree with your entire episode on this, and you didn't do a good job putting your device together either. There, I said it. How do we make them efficient? We're going to talk about that next, because that has been something of a 7-year endeavor for me. Few of you know that, but I've been experimenting with these things, late 2015, early 2016. I've been working on this technology. So why are they inefficient? It's a perception, and it's people not building systems with these correctly. They're not applying them correctly, they're not building the systems correctly, they're not understanding the specifications correctly. All of these things that we know perfectly well within our air conditioning industry. And I'm sorry I have to give a little bit extra emphasis to the air conditioning industry on this one, but I feel like it's time for a technology like this to exist. And I feel like this is a good transitory point for DX and water technologies to have some sort of union, because we have a lot of problems in refrigeration right now, in air conditioning right now, with flammable refrigerants being introduced. And we have a lot of problems with the complexity of water systems. And we have a lot of problems in buildings with waste heat. And we really got to start looking at those problems as energy management of buildings and systems infrastructure. So it's not just buildings, it's systems infrastructure. There's a lot of different things. We got to look at how we better manage our heat. And there may be ways that we can unlock in this chip. So the next episode that I have, so to speak, is, well, how, now that we drew a functional analog, or as you say, Nick, a somewhat complete or near complete functional analog, how would we try to go and start applying that? How might I go build a device that, God forbid I try to compete with you, Nick. How would I go to build a device to get started? What would I do? How would I try to tune it? If I started from one chip and tried to build to where you were, by the way, you're not going to copy me because I already back engineer my own devices and make sure that they have Willy Wonka loop-de-loops in them. So go ahead and try. But God forbid I want to build a chip of my own. How would I go about starting and doing it and trying to make it efficient, as you say, and try to get the results as maybe you do? We're going to talk about that next, because there's a definite way, and there are definite things that you can do, and there are definite things that I can tell you right now that I can get you caught up to scholarly literature right now, and I feel like that's a good place for me, at least, to be with things. I feel like everybody needs to get caught up with scholarly literature on this, because scholarly literature at this point is telling us how to make all of these efficient. I'm not the only person anymore that was sitting on the COP charts looking at these things anymore. You guys need to open up the COP charts for these things. But we're going to talk about that next, because that's not an easy journey either. It's unlocking the COP. There's some stuff that we've got to do. But thank you guys for listening to me. I know this one took on a little bit more of a serious tone, but it's kind of a serious topic. And I think armed with this knowledge and armed with an understanding of this and moving forward, I think that there's a lot of potential that we can unlock in these chips. We have to understand what's going on in the architecture first before we can try to push that architecture. So thank you guys. Been a good one. Wish you a good evening, and we'll go ride my bicycle around.